Okay, good morning again. So you already know me. What we're discussing now is about routing and load balancing. And you will see why we're merging these two terms, because this second one is quite important for us, particularly in our wireless networks of femtocells. But this presentation is mainly about routing, and exchange work with Jose, who will present afterwards. So the way we will share the presentation is we are, I will present up to here, which is more the intro part and how the algorithm works, and Jose will present the evaluation part that he carried out with NS3. And yeah, that's basically it. So as you all know, we are interested in large-scale or wireless networks of femtocells scenarios, and the large-scale word is important in our case, and you will see why, because we're interested, and this poses some design constraints, let's say. And again, all wireless, of course, poses design constraints because we want to minimize the control messaging that we want to send over the network. Well, reference scenarios, airports, conference halls, whenever you have, it may not just be interim deployments like in conference halls, but also in urban scenarios, it may well be a good option, or in rural scenarios even, as in the first day they explained us. And so there are some architectural issues, but the key thing, as I explained in my previous talk, is that we don't want 3GPP specs to be modified, right? Because we are working at the transport network layer. So ideally, what we would like in this environment is to reach these. We will see our design decisions, but ideally, we would like to have an optimal packet routing within this network of femtocells, by which optimal in the sense that we are offering the throughput that users request, and we are serving all the users that are in the old wireless network of femtocells, right? So this is our wish list. Since we are in a large-scale all wireless network of femtocells, we want it to be distributed. We don't want a centralized point of decision, because we are in an all wireless network, which means that we don't want to send too much control overhead over the network. We're going to save resources, and because it's large-scale. So we want to take local decisions. We want it also to be almost stateless, or as stateless as possible. And this has to do with the local decisions, because if we wanted, for example, if we went for a conventional routing protocol in a regular mesh network that calculates routes, so gets all the link states of all the network and then calculates the route, you're sending a lot of control overhead over the old wireless backhaul, and we don't want that. So in that sense, you will see that our scheme mainly uses queue backlog information from neighboring nodes and location information from neighboring nodes. And with these two, and of course the destination that a certain packet wants to reach, we are able to reach the destination and have a certain load balancing and even distribution of resource consumption, right? And of course, as I said, we want it to be lightweight, and we want to distribute resource consumption throughout the network. And this is an illustration of our goal, let's say. In a conventional routing, what you have here is a grid, where each circle is a node. So imagine a network of femtocells like this, in the form of a square, and each of these circles is a different node. So in a conventional routing, where you calculate a given route, what you will have is a certain path that all packets will follow. The code of colors means the number of packets that each node handles. So the more red, more packets are handled by that node, right? So in this case, what you see is that all packets traverse the same route, right? On the other hand, our ideal scenario is that imagine that you have a flow going from this node to this other node, and we would like to evenly distribute resource consumption throughout the network, but not just for this single flow, but for any flow that we may put in the network, right? So, how do we attain this distribution? So we based, we got inspiration from this seminal paper by Tatsoulas and Efremiros back in '92. But that's theory. Let's say we are quite experimental. We wanted something that was deployable and that worked more or less efficiently in an otherwise network of femtocells. So theory says that back pressure is throughput optimal if the flows have rates that are inside what they call the capacity region, which is, you can say it as the set of flows and rates that can be served by a given network. Right? So theory says that back pressure uses the resources best, and if you put flows that are inside this capacity region, these flows will go out of the network without, will be served, will be appropriately served, right? And it's optimal in that sense. So you get everything that goes in the network goes out of the network. But the problem is that it's a centralized scheme. It has some assumptions as any theoretical work, and we wanted to move it to practice. So we are moving from centralized decision points to distributed decision points. We don't want global knowledge of the network. We are, in this sense, we are kind of self-organized, if you want, because based on the local information we are taking decisions. We go from one queue per destination, as the original paper assumed, to a single queue for all destinations, like a regular Wi-Fi interface. From infinite queue sizes that you had in the theoretical paper to finite queue sizes. And in our case, we were specifically interested in seeing what happens when you introduce an unreliable backhaul in the network of femtocells like Wi-Fi. So we want, and this is current work, let's say, this is what we are currently doing, because in this last phase of BeFEMTO, we are now in the, let's say, extensive evaluation phase. We are trying to figure out how far we are from this, by doing all these things, how far we are from the ideal behavior, right? And again, just this is a recap. We are here. Routing is implemented here. So just the transport network layer, if you might recall, what 3GPP defines is the radio network layer, as I said before. So we are putting our routing here. We are taking decisions based on geographic information from neighbors, so the location of the neighbors. We are taking decisions based on queue backlog information from neighbors, okay? And, well, this is the stack of the femto and the local femto gateway. But again, we are constrained to, well, we put modifications inside the network of femtocells and not outside, not the UE, not the core network. And in the transport network layer, same thing. We already saw this one. We are constrained to the network of femtocells. And of course, in our case, we don't have a centralized routing controller. As I mentioned in my previous presentation, we have distributed routing controllers. Well, routing functions, let's say, that we put inside each of the hominode bits, right? So how we describe this routing problem that we want to solve? Like, really briefly, let's say, borrowing notation from stochastic network optimization, what we want to do is to minimize a given cost function, y, the long-term time average of this cost function, y, which in some sense reflects the cost that we introduce when we take routing and forwarding decisions, and it's subject to some constraints. In our case, we want the network to be stable. So this is what the constraint means, which is called strong queue stability, which means that the long-term time average of the expectations of the queue backlogs, that's queue backlogs of the network, the whole network is centralized. So you have an idea of the congestion state of the whole network. That's what queue is at a given time slot, because in the stochastic network optimization framework you use slot time. At the given time slot, is finite. So queues do not grow to infinity, right? Yeah.
You are okay. It's not an Is that really an optimal formulation, or is just a sufficient formulation to say, you know, your network doesn't go out of bound? I mean, but the average could be a value or another value which is bigger. See what I mean?
No.
Is it possible? I mean, if the average Q variation is smaller than infinity, will it automatically be the best you can do?
What theory says is that if you comply with these constraints, well, I mean, they solved initially with the Lyapunov framework.
Yeah.
They solved it initially in this way, like, so they were not as worried for the cost function as they were for network stability. So they took decisions to always minimize congestion state.
Right.
And they guaranteed theory says that if you put input rates inside the capacity region, you get all the flows out of the network with a network being stable. Okay. There are other definitions of stability. You have mean rate, Q stability, well, you have different average, more dealing with averages, more dealing with long terms. Well, depending on the scenario, you use one or the other.
Okay.
Okay. So, well, but this was the basic formulation of the problem. Of course, it's more complex. And there's a really good book by Neely in 2010 on these issues, if you're interested.
And I'm not sure you're going to come to this, but when you talk about geographic, the geo layer, that information is like the X, Y, Z coordinates, or is like electromagnetic distance?
No, it's X, Y, Z.
It's physical distance.
Yeah.
Right.
So, well, you could define a virtual coordinate system if you're interested. This is not, I mean, we were assuming we had it, but there are different ways of doing it. If you are indoors, for example, you don't have GPS coverage, but still you can somehow infer the position. Even if you don't have GPS, you could, like for your network of femtocells, define some virtual coordinate system that somebody configures. We were assuming we had that in place.
Why not bind it to a kind of ETX matrix? Because, I mean, two femtos could be really very close together, one here, one across the door, which is like 10 centimeters, but electromagnetically speaking, they're really lousily connected. And another one, or this one is here, another one is right here, so this is much larger, but they have a much better connectivity.
Yeah, this is part of the next step that we plan to do. I mean, for now, what we wanted to do is to test if this idea of combining geographic information and Q backlog information was good enough to attain certain goals. Next step is to improve that with metrics like the one you mentioned.
Well, in fact, exactly, it will not influence, will just influence
it's
via
kind of
which one it will go.
If you want, it will modify your cost function and all that. We plan to do that.
Okay, very interesting.
Yeah. So as I said, initially, if you just take into account the congestion state, so Q of the whole network, so you add somehow the congestion of all the networks. So there's something called the Lyapunov Optimization, which is reflected in this first term, which is this thing over there. So in simplified form, right? It's just to illustrate. So what this represents is the difference between what you could call congestion states of the Q sizes of globally in the network, right? So you have one certain congestion state in time slot t, and you have a different one in the next time slot. Right? And this is the definition. So it's defined in a way that if you have a single Q which is quite backloaded, then this L function is quite high. If you, for having a low L, you would have all networks Q backlogs quite low. Otherwise, it will be high, right? That's the message. So what they did to stabilize the network, as I said, was to greedily take decisions at each time slot to go to a lower congestion state. So they have a complete view of the congestion state of the network, and in each time slot, they take the control action, so whatever routing decision or whatever you are doing, so that you reduce and you evenly distribute the load throughout the network. You try to go to a lower congestion state, right? So that's the main measure. And in this way, you get network stability. But with that, you just solve the network stability issue. You don't put any like cost function in place. And the way the Lyapunov optimization solves this issue is by adding this other term that somehow matches this cost function that I was mentioning before. The y function somehow is mapped to this penalty function, and furthermore, it's weighed with a parameter v, which is the one that will determine what is the importance in your decisions that you assign to network stability, let's say, taking decisions for distributed resource consumption, and what is the importance that you assign to your cost function, right? So in this case, what they showed is that by appropriately tuning this parameter v, Theo says again that you can reach as close as possible to the optimal, for example, imagine that your cost function is delay, you could be as close as possible to the minimal and then optimal delay in the network, but at the cost of linearly increasing the Q backlog. Right? That's what the framework says. And you will see some results on that afterwards. But again, this was the centralized part of the story. Now we're moving to a distributed routing algorithm that allows us to communicate between any two nodes, which is based on this framework. And for that, moving into a practical framework, we tried to do the same at a local stage, not in a centralized level, but only based, taking the same kind of decisions that I just explained, but at a local level, right? Each node based on the local information it receives from neighbors. And that's why we define these ways. So we still have this Q drift, which is the difference between, imagine that we are in node I, this is the one taking the decision, and J are any neighbor that we may have. And we calculate this Q difference between our Q backlog and the Q backlog of each of our neighbors. And besides, well, there's a minus sign, but it depends on how you define the penalty function in this sense. But the basic idea is the same. You still have this weight parameter, and you have the penalty function. And here is where we introduce the geographic information, which is quite simple in our case, because, as I said, we were mainly interested in testing the functionality, if it works or not, right? So in this case, basically, we are like our P is equal to +1 if there is no progress to the destination. So our node is closer to the destination than any other neighbor, so there's no sense in forwarding the packet, let's say, unless it is for resource consumption, and the other way around. If we have some progress towards the destination, we have a minus there. So what we want, ideally, is to send packets to the less congested neighbor. So we're interested in having this value as big as possible. So if we are congested and the neighbor, we will pick the neighbor that is less congested. And we're, of course, interested in reaching the destination. So overall, we will pick out of all our neighbors the one that gives us a higher weight. And that's the way we take the local decision, let's say. But yet, in part, in the same way we took decisions, well, they took decisions in the centralized theoretical approach, right? So, yeah.
If you go back to one slide back, I think, here would be this P could be fantastically replaced by the concept we're doing in ITF role. Okay. Because it's, you get rid of the geographical information, you rather build in essentially the electromagnetic distance, and via the ETX, well, you can build it as you want. You can build it in Q length or whatever. And And you can also, since you anyway piggyback information forth and back, the queue length you have to exchange with your neighbors, you can always update your rank in the system and get really a completely autonomous system.
The key about this, I mean, we were also considering putting energy considerations in there. If you are in a sensor network, for example, what's the energy that you have in neighboring nodes? So P is fantastic for that.
Yeah, exactly.
I mean,
balance.
And the other nice thing is that, as you will see in some other results, is that you can play quite a lot with V, and to depending on how the network, how interested you are in weighting a certain way of working in the network, or in weighting network stability. So well, you can adapt that nicely with V.
Okay, and then a question, which we have been discussing through various presentations throughout this week. How do you know that constructing the weighting factor this way is a good way or is an optimum way? How, why not a square? Why not the absolute value, square root, whatever? Why a linear difference and a multiplicative with the, where does it come from?
We wanted something basic, which means implementable, and so that we can take conclusions. Maybe we can have more complex values, but the basic reason is that the framework, the Lyapunov framework, defined it this way. And we saw some papers applied to sensor networks, for example, that were going this way. They were applying these for mainly for uplink traffic gathering, to the gateway. We are extending that to any, and they found that this approach was good enough to have a more or less practical system. So it's a consideration between what the framework initially proposed, what these guys did, which was more or less practical, but did not suit all of our needs. Well, it's a combination of all this.
Okay.
So this is the way we take the decisions, as I explained. So we take the higher weight for all the links, but only calculate based on local information. And we do sort of, the other nice thing about this protocol, particularly for an all-wireless network of femtocells, is that we do sort of network layer scheduling, meaning that unless the weight is greater than 0, we don't transmit a packet, which means that if we know that all our neighbors are congested and we don't get any advantage of sending the packet to our neighbor, we don't send it, so we don't consume resources. So this is kind of a nice feature of the protocol. We wait for better opportunity to transmit, right? And of course, in a Wi-Fi environment, you still have this layer 2 scheduling, right? So, and this is to illustrate what you can do with V. So by playing with V, and this is again the certain grid, and we are sending traffic from this node. That's why it's black, because it's handling more packets. And you go down to white, which means that no packets are handled by these nodes. So what you see, if you have a low V parameter, meaning that you mostly take decisions based on queue drift, what you do is you distribute resource consumption. So you're evenly distributing packets only based on the congestion state of neighboring nodes. But if you're more interested in putting packets as quickly as possible to the destination, you can have a higher V or an even higher V. And what you see, it's clear the effect from the figures, right? It depends on how you weight each of the things.
Have you tried to generate traffic in all of the nodes and vary maybe the propagation characteristics?
Jose will show some graphs
Excellent.
afterward in simulations, in some simple scenarios. Now we are with the exhaustive, and we already have some ideas for improvement, but you will see some results with various flows to illustrate the results. Yeah. Jose has carried out simulations. So this is about the general overview of the protocol and how it works, and just quick hints that we already discussed about that. Let's say that we are working at the transport network layer, no implications, but we add this geo sublayer. there might be some other issues, particularly if you want to benefit of having multiple local femto gateways on a wireless network of femtocells, and you are interested in allowing that traffic from different UEs use potentially, or even from the same UE, use potentially all these local femto gateways at the same time for load balancing purposes, then there may be an issue because you might recall that the local femto gateway has a barrier established with the homing node B. So this means that in the end, the packet must reach the original local femto gateway. So if you go out of the network through a certain local femto gateway, what we are assuming in this case, for example, is that you have a wired connection that makes the IP packet reach the appropriate local femto gateway. Well, there are some issues related to that. And of course, our routing protocol allows you to establish these flows that I was mentioning before, where you could have traffic from a given UE inside the network of femtocells to its serving femtocell, to the target femtocell, and to another UE. Our routing protocol would allow that. Of course, with the local location management and associated mechanisms would allow that. The problem is that 3GPP specs currently, as far as we know, they do not allow you to establish a permanent X2 bearer for sending traffic in this way. There are also legal lawful interception issues also in this kind of scenarios. But anyway, this was just to highlight that there may be some implications that we are handling in the project. And as I said, this is maybe the most dangerous flow, let's say, to serve if you want to comply with 3GPP. All the rest, more or less, we can handle them. And now let's move on with the evaluation part, which Jose carried out. So he's, let's say, one of our best research engineers in the area. So Jose is working with us. He's also running running for his PhD with us. And he was working also at UPC, where he worked in several projects, Saba and many others, and now he's with us mainly working in NS3. He's an expert in NS3, as you will see in the following presentations also, not only in the simulation part, but also in the moving it to the testbed, because as you will see, we have some nice results about the testbed for that. And that's it. So, Jose.
Okay, so now let's gonna see how do we evaluate the routing protocol on a high-scale Wi-Fi backhaul in order to satisfy the traffic requirements of an all-wireless network of femtocells. Okay, so first of all, we will see a study that we make with having the B parameter having a fixed constant B parameter, and then we will see results that we have carried out with a variable B algorithm in order to auto-configure every home node B in the all wireless network of femtocells depending on the traffic requirements with a higher, lower, or medium B. So I think this may be related with your previous question, Misha, because as we will see, depending on the number of flows that you inject to the all wireless network of femtocells, having a fixed B parameter in the network for all the home node Bs is not a good policy. So we will see afterwards our current work on this variable B algorithm. Okay, so this is the setup of the NS3 simulator in order to see the effects of the configuration of a fixed B param routing policy. So what we've done is to inject, in this case, two flows in the network of femtocells, and we measured in target network performance metrics with this simple penalty function, which is the relative distance to the intended destination. So basically, we injected two flows and we carried out several experiments varying the traffic injected to the network of femtocells between just 1 megabit and 6 megabits for every flow. So we consider as technology for the backhaul low cost and licensed spectrum based on 802.11a, configured to 54 megabits, and we configure the Wi-Fi MAC layer so that no hidden nodes are attained. Okay, so we don't have propagation errors. We just can lose packets due to queue drops in the home and bits. So this is a simple setup in terms of wireless propagation and wireless errors. Okay, these are the results we obtain with in terms of throughput at the intended destination. As we can see here, over the x-axis, we project the B parameter over this range, which, as we will show later, cover all the possibilities for the B parameter because of the queue backlog that we configure in every home and B. And we can see the variability of throughput over the x-axis with this B parameter for different input rates for the two flows injected in the network of femtocells. And as we can see here, for low B parameters, as we are not giving too much emphasis on the penalty function, we are not getting closer to the destination, and you have kind of random routing merely based on minimizing the queue state on the home and Bs. So this is not a good choice, as we can see here. Then, as you increase the B parameter, you see how you achieve the offered load injected to the network of femtocells. Within this region, we attain a good trade-off for these offered loads between the penalty function and the minimization of the queue backlogs. But also, as we can see here, as we increase the B parameter, we are giving too much emphasis to the penalty function, and we are getting queue drops, especially in this case, for the offered load of 6 megabits. So we do not get the 6 megabits. Yeah?
Okay. If I go, just thinking back to Giuseppe's graph, you have you assume more or less one source, one destination.
In this case, two flows.
Okay. I think conceptually it will change a little, but I mean, in fact, the bottleneck is always, let's say, on the useful data rate which arrives at the destination. The bottleneck is the final wireless interface at the receiving side. Okay.
Mm-hmm.
So if you had a medium access control, which is really like time scheduled, everything is able to, the incoming traffic is served as it's going out, not hitting the saturation rate, you would, no matter how you would schedule it, it would always come through. I mean, no matter how the flow goes, it would always reach it. And this is in fact what we see here.
This is what we see here.
Until region, you reach the 6 megabits per second, where I think CSMA type of paradigms start to kick in. This is what my suspicion is, why the V500 very large, you start to spread out the traffic. So congestion to any node increases automatically.
Yeah.
So therefore the CSMA of your .11 starts to kick in, so you get this automatic curve.
Exactly.
So I think the interpretation might be different. It's not related to the queue, it's simply related to the medium access control.
CCMA, what happens here is that in this region, as we go to, let's say, single path to the destination, what happens is that you say, CSMA experiences a lot of congestion, and this incurs into higher queuing in the nodes, because they have to wait more time in order to get idle mode to transmit. We are saturating, let's say, the same network zone in the all wireless network of femtocells.
Okay.
Going back here is like having just this, the set of nodes of the indicated by.
Oh yeah, I understand. Yes. Well, with V, yeah.
Then you
With
have
V increasing, exactly, you increase the probability of congestion.
exactly.
In a sense, because you're traveling along a narrow data path. So that CSMA kind of paradigms, even though not versus the traffic, but versus, let's say, the density of the traffic is starting to kick in. Okay.
This doesn't mean that here we do not have problems if we have hidden nodes. Because you are using the whole network and all nodes are trying to transmit at the same time, and so it has another issues, but we assume a network without hidden nodes.
Well, I don't see a sense of having a small V if the traffic can flow through a narrow data pipe. I think I would adapt maybe the V in dependency of the amount of traffic you.
Exactly.
Okay, you do that.
If the load is
very low, you have a high V,
it's
and
light,
and if
the
you have
good
a.
thing is to have a high
Okay.
V.
Okay.
So coming back to this graph, well, this is what we have seen. Basically, low V means random walk of packets through the backhaul. Medium V seems okay. We kind of achieve a good trade-off between the both components, Lyapunov drift and penalty function. Very high V, be careful with if you increase the overhead load. You can experience CSMA congestion and so Q drops. What happens with delay? With delay, happens for low Vs, happens somewhat similar as what we have seen with throughput. Packets are kind of making a random walk over the network, and they do not get to reach the destination. And those who achieve to get to the destination experience high delays. But as we increase V, and as Neely proved, the network performance metric, the network objective function in this case, evolves with the inverse of B. But also here, Neely proves that assuming Q backlogs infinite, your delay will grow linearly with B. But since we have low and finite Q backlogs, we don't experience this degradation on this graph. So in terms of fairness, what we plot over the x-axis was the 24 different experiments in terms of injection of data flows, and we wanted to see the evolution with the V parameter. And as we can see here, two facts affect the fairness that we can get between the two flows injected into the backhaul. One is the V parameter, and the other is the kind of the input rate matrix that you inject, which depends on the location of the source destination pairs. So basically, you can have variations with your V parameter, and you can have variations as well with the input rate matrix index. With a very simple example, we can understand how this thing is happening. For instance, let's see a network in which two flows are injected towards the same destination. What happens here is that as you achieve a decreasing Q backlog gradient to the destination, because both flows are directed to the same destination, you do not experience too much congestion. But in this case, in which we have bidirectional traffic, packets from one flow are fighting with packets from the other flow. to reach their intended destination, because here traffic injected from this node is trying to reach this node, which is also injecting packets. So we have kind of contention between packets that makes it difficult to reach their respective destinations. In order to solve all these kind of problems, we thought that it would be good to change this B parameter from a fixed constant to a variable B algorithm. And which was the purpose of all this? We take a look at what happened in the previous study, and we saw that we have problems with bidirectional traffic. On the other hand, traffic demands for every node do not have to be constant. Every homonode B, yeah? Network coding?
Did you assume also that when you have bidirectional traffic, you can use network coding, so you can avoid that problem with traffic congestion?
Yeah, but the problem is that here we have a flow going to this node.
Yeah.
And this node is injecting a flow
but when you,
to this node.
Yeah, but when you are using network coding, you can code two packets into one in a bidirectional flow, so you reduce
we can
traffic.
Reduce the number of packets. Yep. Okay,
that's one possibility.
Okay. So not for redundancy, but for let's say mixing. But you are gonna generate the same number of packets.
No.
What you can do is do packet aggregation. Maybe if you had packets of lower. Of
no, you
size.
have less packets than in network because you code two packets into one.
Yeah, but you have to do two random combinations of the two packets. At the end, you need to decode information. Random coding is not magic. I mean, if you have two packets, if you had to send two packets, you cannot just send one packet unless it's of higher size.
Yeah, but
you will have to send two packets. Code the two
no,
packets.
just one.
Just one.
Yeah, but
and
when you are coding, then you send just one packet, which means that you have two packets in one, and you have only one transmission. You know, when you have bidirectional flow, you can code two packets into one, which is coded, and you then transmit just one.
But then you have to decode the packet.
Yeah, but that's on the that's on the node, you know, when you decode. So you don't have then problem in the channel, in the congestion in the channel when you have coding is appearing in at node. You know, that's a computational problem, not congestion.
So with less packets, you may decode.
You have less packets on the channel when you use network coding in bidirectional flow.
Without incrementing the size of the packet?
Yeah, only the information for the coding.
So if I send two packets here, A plus B, I do by XOR, and then here, but here I will need B in order to decode A and B if I have AX or B.
I think just maybe, I mean, network coding, on the very specific topologies really gives you, a bandwidth savings. But if you average over all possible scenarios, maybe with more than one sink and more than one source, you don't gain so much in spectral efficiency, what you have been discussing, but rather in outage. So that the network becomes much robuster, which I think is a completely different optimization criteria. So maybe you can take this discussion offline.
Yeah, okay.
Yeah, okay.
Yeah, okay.
You wanted to say something? It's okay.
Okay, so coming back to the... thanks. Going back to the variable V algorithm, the goal of this algorithm is to be able to auto configure the V parameter in each homonode V in function of the local offered load or the local congestion in the network of femtocells. So that at the end we have a distributed variable V controller that doesn't need the intervention of any administrator, let's say, to put there the value that you need to auto configure the V parameter, to configure the V parameter. So ideally, what we would like in this variable V algorithm, we would like to maximize the penalty function if we can, but without incurring into Q drops, and also without incurring into high queuing delays. So on the one hand, we want to get the maximum V parameter that we can get, and also without incurring into Q drops, so that intended network performance metrics such as delay, throughput, reachability are optimized. So a good rule of thumb will be to increase the V parameter if there is no local congestion within the one-hop network of femtocells, within the one-hop neighborhood, or decrease the V parameter when there are problems of congestion, so that we go within this zone of load balancing, maximum degree of load balancing. How do we do that? So basically what we do is to build a virtual queue that estimates the congestion within the next time slot, in the next time slot. To build this queue, we take two components: the maximum queue length of the one-hop neighborhood and the maximum queue incremental experienced by a neighbor queue, which approximates the increase in the offered load, in the potential increase of the offered on the local offered load in the network. And basically, we sum both components here, and this is an estimation of the maximum, in the worst case scenario, maximum queue that we will have on the next time slot. And the remainder to reach the bound of the buffer size is our V parameter. So here we have an example, in very simple example, in which we have two flows. One injected, here we have two saturating flows, one injected at instant 5 seconds, another flow injected at the instant 20 seconds. Here in the left graph we plot the evolution of the V parameter in time, and on the right graph we plot the evolution in time of one of the target network performance metrics in a network of femtocells for different instance of the V parameter and the variable V algorithm. And as we can see here, at instant 5, we have the maximum. So we are greedy in terms of the penalty function with when there is like load in the network. And so we are giving maximum priority to the penalty function. At instant 5, there is this saturating flow at the reference node. And what the home node B does is to auto-configure the B parameter to increase the degree of load balancing, which means increasing decreasing the B parameter. Then it goes in a, let's say, variable state, which depends on the distribution of traffic that is coming here around this region, until we get into the instant 20, in which another flow is injected into the closer network. What happens here is that the reference node says, okay, I cannot handle this offered load anymore, and I'm going to configure to myself in maximum load balancing. So B equals 0. And the flow finishes at instant 60, and then the reference node detects that there is a decrease of traffic in the one hop neighborhood and increase the B parameter. So at this region, it is still able to handle it's able to give priority to the penalty function. Well, and so forth. And instant 80, the flow 1 is finishes, and it configures itself to the maximum degree of greediness in terms of the penalty function. In terms of delay and packet delivery ratio, we plot the distribution of packet delay, and we saw that for the fixed B policies, we lose packets, and because of Q drops, and we experiences high variability in terms of packet delay. But for the variable B algorithm, we experiences lower variability, and we observe maximum delays. And so with this packet distribution delay, we also are able to get all the packets. So as conclusions, we have seen current work on the distributed routing algorithm for the all network of femtocells. These are the properties. We have seen that as we have evaluated the protocol in a 100 all wireless network of femtocells, it's scalable, it's distributed, quasi-stateless, we need just one hop network information, and it's transparent to 3GPP procedures. In future work, we would like to focus on the Mach medium characteristics and come up with different penalty functions, because at this stage we are agnostic of the Mach medium that we are handling. Okay, so that's all.
Very good. Jose, any questions? We had a lot of discussion in between already. So yeah, just a general question. I mean, you seem to have, you build your cost function, let's say, around a few parameters, and one of them being the V parameter, and you realized, okay, let's this seems to be important. You've done loads of studies around it. Mm-hmm. So my question goes again back, as I said before, is, how sure are you that this is the right parameter to look at, and then in the right way? Well, it's a more philosophical question, but it's before. It's interesting to get this to know before you really
you mean
start.
The form of the
parameter? Yeah.
Well, it comes
because you accept it somehow. You accepted it. I'm not sure whether you've ever wondered playing around with other cost functions, but what the result would be like.
This was the result of the optimization problem approach on a centralized network with several assumptions, and we take this the solution of the optimization problem, and somehow
it works.
Trust on this parameter, and but as we have seen here, it has problems if it's constant. We have seen with this bidirectional flow that it can pose performance degradation on the performance metrics, and we in fact we are changing the from a constant B parameter to a variable B algorithm.
Yeah, no, what I mean is you may want to play around a bit with the function. I've done the same comment to Paul, for instance, or to Lorenza, I can't remember, on the Q-learning algorithm. In fact, there are lots of similarities in there, and they changed the cost function, and suddenly things changed. So the convergence was quicker, and the system suddenly was operating more optimal. There's no rule. We don't know how to construct it. It comes back to the same problem. But maybe it might be worthy looking at, other type of dependencies. I'm not sure you want to add to us.
What you're suggesting is that we should instead of a linear function. Quadratic. Okay. Okay. Yeah. As I said, this is the first approach. I mean, we didn't take a look much in the theory. We wanted a practical system, so we took what was available and we solved the issues that remained to have a practical system. Now, in the background, we are starting to consider all these more, let's say, theoretical or the rationale behind each of the parameters, what's the best function, new penalty functions, and all that stuff. Now we have the framework, and now we can play with many of the parameters of the framework, But the results initially are promising. I mean, the combination of the Q-backlog information and also the geographic information, I mean, for the setup that we wanted, which is a large-scale wireless network of femtocells, I mean, it suits our needs initially,
Thank you.
Okay, let's see
so some links in your model have link utilization like 1 or 100%, and then you change the routing on other.
It's a reliable with contention medium. Let's say the evaluation.
Some links has link utilization like 1, like for the max. Okay.
The only way to get packet losses here is due to the Q drops in this simulation.
Okay.
So the other nice thing, and maybe I didn't emphasize it enough. The other nice thing about these protocols is that you take decisions on a per packet basis. So you don't have routes, as I said, but so then you can always when I want to forward this packet now with the current status, I decide to go this way. With the next packet, I take a look at the environment and I go that way. So that's the. No routes. That's why we only use local information, and the nice thing about exploiting geographic information is that you can still reach the destination, but with less states in the nodes, and just taking a look at your neighbors.
Of course, you need to insert in the header of the packets the destination coordinates of the home node.
Regular geographic.
Okay, that's it. Then thanks. So what's the plan now? Okay, we have a we have a very, very small break, 5 minutes, and then you shoot,